Thank you. My name is Arturo Castillo, based at the Center for Environmental Policy, and I would like to talk to you about the challenges of plastic pollution, as well as the rationale for intervention, which can happen by using some of the technologies that my colleagues will present. The first thing to do is to remind ourselves of the complexity of the plastic system. And that is because we have many functions in society for which we need plastic, and they range from food preservation to clothing, all the way through to clinical equipment. On the next step is that we have different plastic polymer types. And in some cases, you can use more than one of these polymers to make some of those products that satisfy some of those functions. Then on the next step, we have other substances or chemicals that are added to enhance some of the properties of the polymers. And that can be for reasons of appearance, flexibility, flame resistance, and many others. And as you can see already, the combinations and permutations can also be very variable, and many combinations available on the market. So that is also a challenge when we try to take one of these products and we try to assure the quality of the material recovered when we put a product or a material through a recycling system. So this is just to illustrate the complexity of the global supply chains. Now, plastic is a great material, as we just saw, and that also gives us a great responsibility. Now, we can see here on the left-hand side that plastic has some great properties that makes it so popular. For example, it is durable. It has a very high strength-to-weight ratio, and this is the reason why up to 50% of a modern aircraft consists of some kind of plastic polymer. Then we also have moisture and oxygen barriers, and that's the reason why it is very good for food preservation. And then we have lightweight, which is very good for transport. And of course, very importantly, it is low cost, which makes it very hard for any other material to compete in many cases with plastic. So those are the reasons for the popularity of plastic that we can see reflected here in the growth of global annual production of plastic. And you can see that you need to consider that population growth combined with globalization gives you the result that there are more and more people between now and 2035, probably, and everybody consumes more on a per capita basis. So that results in this shape of that curve. Then we have that great responsibility that can also pose a great challenge. Now we need to remind ourselves what happens when in a high-income country, somebody like us can decide that they no longer want a product, and suddenly that becomes a nuisance. But we can all afford to pay somebody to come and get rid of it for us, and also we can afford to finance and manage different kinds of infrastructure to deal with it. Those different infrastructures allow us to reuse or recycle in some cases, and then in other cases we can manage the waste by incineration or landfill or other technique. A very important question is what happens when this affordability is not there, or this ability to afford this infrastructure is not there. And that is what happens in many other parts of the world, where people still need to feed and clothe themselves, but they don't necessarily afford those kinds of infrastructures. So then the reality looks a little bit like that, and that's where ocean plastic pollution starts. On land, we know that around about 80% of all the plastic that is in the ocean originated from land-based activities. So we have a very tough challenge because there is no easy drop-in substitute. We know that whatever we want to substitute plastic with is going to have some trade-offs and some costs, and this is really a zero-sum game that we're faced with. Also, in the environmental social sciences, there is a very interesting rhetorical question about affordability. And it says something like this. It says, if it's all about affordability, does that mean that people who can afford waste management systems can continue to waste? And does that mean that those who cannot afford waste management should consume less? Now, of course, this is a rhetorical question, but it helps us to frame the problem, because then we realize that it cannot be all about pointing fingers to people who cannot afford the waste management. It's also probably a lot more to do with the disconnect between the pre-consumption side and the post-consumption side. And that will become clearer in the next presentations as well. So that challenge is sort of difficult because it comes with all the different health and environmental impacts that resulted from that situation that I just presented. And these impacts can be classified in physical and chemical harm. And I'm sure that a lot of you have seen a lot of the pictures of marine mammals and seabirds that are affected by some of these kinds of damage, like, for example, starvation by blockage or tearing of the gut. They can be choking and entanglement because of discarded fishing gear. And also a different kind of physical damage is that plastic debris can, when it is on land, can obstruct drainage systems, causing flooding. Now, on the chemical side, we know that there are many chemicals that are added to plastic, like bisphenol A and polychlorinated biphenyls. And those have been linked with endocrine disruption and a couple of other effects that have been observed in fish populations, but also in other laboratory-based studies. And also we're starting to get some evidence in some group studies for using human beings because of epidemiological studies, but it's still early stages. Now, amongst these effects are developmental, neurological, and reproductive effects. And also one kind of research that is also taking place at Imperial College at an early stage is studying the potential for damage caused by inhalation of nanoplastic particles in the atmosphere. Now, following on from those types of harm, we also have other reasons that are compelling for research and action. So we also have economic impacts that people in many sectors are already starting to feel very tangibly. And we have, for example, tourism and well-being are being affected by pollution and this amenity. The shipping sector is being affected by damage to some of their vessels. And fishing, particularly in low-income countries, is affected by discarded fishing gear. And also we lose a lot of the value that we invested in making products at the time when we burn them or dump them, or those products are leaked to the environment. So in terms of looking ahead to what is going to be presented at the rest of the event and then all the different technologies, I have some questions here that probably will help us think ahead of what we should be doing with all these interventions. And they are things like, how might we further link materials to sustain value? Another one is, how might we increase material recovery? And also, what are the externalities of inaction? Now, as you will see in the next presentations, we have covered in the Greener Plastic Futures project, technologies like multi-level plastics, multi-layer packaging, mechanical and chemical recycling, and also better use of additives, amongst other technologies. So with that, I will bring this introduction to a close, and I look forward to the question and answer session. Thank you.
Hello everyone, I'm Manu. I'm a postdoctoral researcher working in the Department of Mechanical Engineering. My research focuses on improving the recyclability of some of the hard-to-recycle plastic packaging. Today, I will discuss a bit on the plastic problem from packaging perspective and some solutions that can help address the challenges that we face today. Plastics are engineered material made to be versatile, robust, and low in cost. As a result, plastics are used in almost every industry, and they stay in our environment for years even after their intended use. Even though plastics are used in many applications, packaging industry dominates. If we look at the visible plastic pollution around us, we can see that product packaging, especially from retail, dominate. Shown here is the breakdown of items collected during river cleanups along River Thames by Thames River Watch in 2017. We can see that most of the pollutants are packaging items. There have been many positive changes to improve this dire situation, mostly through substitution by alternative materials. But there is little to no evidence of meaningful actions across the packaging portfolios to address major plastic pollutant, that is, flexible plastic packaging. There is an increased awareness on plastic pollution and its effects among us, thanks to various media outlets and campaigns spearheaded by inspirational individuals. As a result, we can see a greater number of river and beach cleanups, as well as innovative solutions to address plastic pollution. Plastic pollutes from the extraction of its raw materials and after its end of life. Therefore, reduction, reuse, and recycling of plastics are the only viable solution to limit pollution. Even though we have made some progress in this regard, a lot more has to be done to reduce the reliance on plastics. Unfortunately, the demand for plastics are only increasing, despite our efforts to recycle and reduce the amount of plastics used in packaging. The global packaging industry is predicted to have a continued annual growth rate of 4%, and the market for flexible packaging are also predicted to follow the suit with the increase in population, purchasing power, and consumption. A typical example would be PET, from which bottles and some fabrics are made. This type of plastic has good recycling rates among packaging, but the PET production is projected to grow to meet the increased demand. Plastic pollution is one of the biggest challenges faced by humankind, and rightfully, there is an urgency in resolving it. As a result, plastics are seen in a bad light, despite the multitude of benefits and convenience they add to our daily life. Whilst there are many avenues to eliminate and reduce the use of plastics, they are irreplaceable in some applications. An example would be multi-layered packaging plastics, or MLP. As the name implies, they are essentially layers of different materials, mostly plastics, stuck together in a laminate form, and they are mostly used in food packaging and pharmaceutical industry. The multi-material construction allows to meet various packaging requirements. A typical construction is shown here, where functional layers A, C, and D are tied together by means of a tie or adhesive layer. The outer layer A provides mechanical support and printability. Layer C provides the essential barrier protection against light, moisture, or help maintain an inert atmosphere inside the packaging. Layer D provides the ability to seal the packaging around the product. Depending on how the packaged product is distributed, MLPs can be as pouch films, top webs, or thermoformed trays. As consumers, we are very familiar with these type of packaging materials. For example, packaging for prepared meals, fruits and vegetables, confectionery, snacks, etc. By extending the shelf life of the items packaged within, this packaging products increases the efficiency of the resources that went into producing these items. When properly disposed of, these plastics are collected by waste management services. The capabilities of recycling vary locally, but due to the diverse nature of MLP laminates, they are not reclaimed and sorted like waste materials of single polymeric type, such as bottles. Instead, these are landfilled or incinerated, neither of which yields a new material that could be used again. We can identify some main factors that limit the effective recycling of MLPs. Currently, sorting technology can only identify the polymer facing the sensor. This often leads to incorrect sorting at the material recovery facilities, as MLP have more than one type of polymers. Packaging typically features bright and contrasting colors to attract consumer attention. Melting into liquid form and processing different colored plastics results in recycled materials with green or dark gray in color. Melting and blending different polymers, metals, and additives also results in low material properties. This also limits the reuse potential and represents low value for recyclers. Only a small portion of reclaimed MLP is recycled, and also often in very low-end applications such as garden furniture. Sorting and recycling technology for the individual polymers that makes up MLP are highly developed. However, the strong adhesion between the layers in MLP means these layers cannot be separated and processed through those means. In a way, the multi-material construction is limiting its recycling potential. To this effect, there have been many research into reducing the packaging complexity and also on advanced materials capable of providing multiple packaging functionalities in a single material. However, these monomaterial configurations are not as effective as MLPs in more demanding environments. In short, MLPs are here to stay, so we need to develop solutions to facilitate their recycling. Fortunately, there are emerging recycling strategies for MLP and flexibles within mechanical and chemical recycling. Panos will cover more on the chemical recycling in next presentation, so I will focus on mechanical recycling. Here, materials are broken down by mechanical means such as shredding and shearing, retaining their polymer structure. This is followed by melting into liquid form and blending. Mechanical recycling is the dominant recycling method for plastics. Therefore, it is advantageous to pursue options within this for MLP and flexibles as well. As I mentioned earlier, main challenge is the low mechanical and physical properties of MLP when recycled in this way. This can be mitigated by means of two distinct but mutually beneficial approaches, blending and layer separation. One approach to improve the mechanical properties of recycled MLP is to add fibrous reinforcement into the blend of polymers, so as to have fiber-dominant properties from the resulting composite. Downsides are that carbon fibers are often required to offset the properties, and it only adds one additional life cycle. Further recycling of composites are also challenging. Different plastics have different properties, and they cannot be easily blended in its liquid form. This is one of the limitations in recycling MLP through conventional melt blending techniques. Compatibilization involves adding a surfactant polymer to enhance the interface between different polymers. The mechanical properties of the recycled materials from MLP can be improved through this method. Layer separation strategies can be seen as a subset of design for recycling initiatives, where the laminates are designed so that they can be separated during the recycling steps of shredding and washing. This is especially useful for separating MLPs with metallic foils, such as crisp packets, because the presence of metal usually results in low material properties in blending approaches. Layer separation can be achieved by using a special layer in between that softens, swells, or dissolves in a solvent. It can also be achieved by controlling the levels of adhesion by modifying the surface treatment carried out on the layers. Recycled materials struggle to be cost competitive with virgin polymers from petrochemical sources. Lack of proper collection and sorting limits the availability of good quality MLP for recycling and adds to its cost. Sensor-based sorting technologies are on the rise, perhaps providing separate collection for flexible packaging or incentivizing their return from consumers to collection points can also make a big difference in producing sufficient amount of flexibles that are sorted by default. Improving the mechanical and physical properties will create value for recycled materials. However, policies that enforce and encourage use of recycled materials are also essential to create demand and sustain a market for recycled materials. Plastic packaging are typically developed to meet the packaging functions at the lowest cost. This has perpetuated the throwaway culture that is contributing towards the environmental plastic pollution. Therefore, it is imperative to develop packaging that are easier to reclaim and recycle without compromising its quality. Surely, elimination or reduction of plastics where they are not essential are non-negotiable to reduce their pollution. As for applications where they cannot be replaced, effective recycling is the only viable solution to reduce pollution. Technological solutions alone cannot prevent pollution. We want manufacturers to move away from single-use plastics and make sure their packaging designs can be widely recycled. We also want to develop strong recycling industry to manage and reprocess the waste generated here. We need robust policies in place to enforce and encourage manufacturers to use widely recyclable materials in recycle-friendly configurations. We have to dispel consumer misconceptions about recycling and change negative consumer perception on products with recycled materials. We are all consumers, and we can use our combined purchasing power to demand retail initiatives that are aimed to reduce plastic pollution and support them. This presentation only focused on flexible plastics and packaging. Plastics from other sectors, mainly agriculture and fisheries, are also higher up as pollutions. Plastic pollution is a complex and multifaceted challenge, and it requires expertise and commitment from different avenues to solve it quickly. Thank you all for listening. I would like to thank Soft Solid Group in Department of Mechanical Engineering, as well as my colleagues from Imperial working on this project. I would also like to thank UKRI for funding my research, and also to the Institute of Molecular Science and Engineering for giving me this opportunity. This concludes my presentation. Thank you all again.
My name is Panos Beksis. I work at the chemistry department of Imperial College London. I'm a postdoctoral research associate. I want to start by thanking everyone for attending this event, and also thanking the Institute for Molecular Science and Engineering for giving us the opportunity to write this paper and give you these presentations today. Okay, so today I'm going to talk to you about pretty much the projects I've been working at Imperial College, which relates to the paper as well. And they involve new approaches for efficient polymer compatibilization and non-expensive chemical recycling and the development and synthesis of biosourced or recyclable high-performance materials. So I'm pretty sure you all know, and as Manu and Arturo already commented, that plastics are all around us by now, and their production is actually expected to double in the next 20 years and almost quadruple by 2050. By this time, it is estimated that 20% of world's total oil consumption will involve plastics. Plastics can be used for many applications. Packaging is by far the sector with the largest usage. It's actually more than the second and the third largest sectors combined. So as far as Europe is concerned, it's sad to report that only almost a third of all the plastics generated are recycled nowadays. The rest either ends up in landfills or is incinerated with partial energy recovery, mostly mixed solid waste incinerators. So this is obviously a problem, an environmental problem. So there are courses of action suggested by Imperial College and actually are researched right now. So there are various research groups at Imperial College which are currently researching how can we reduce this amount of plastic, this large amount of plastic leaked into the environment. We try to come up with or suggest new policies or better commercial and civil practices, or increase the awareness of the public regarding resource efficiency. We're also developing new technologies that are responsible for recovering polymers and monomers. Monomers are the building blocks, the constitutional building blocks of the plastics. And also, it's worthwhile to involve all stakeholders to actually rethink how we can reshape the manufacturing of plastics in the future with the aim of reducing their toxicity or increasing the amount of plastic that can be recovered by recycling. So the first part of this talk is about polymer compatibilization. Compatibilizers are chemical compounds which are specifically designed to act as some sort of molecular stitches between the interface of otherwise immiscible or incompatible plastics, which can be found in a mixed plastic waste. The interesting fact about compatibilization is that it can be used alongside melt processing to effectively recycle exclusively polymeric packaging. In packaging materials of the food and healthcare industries, we have often the issue of metallized layers, which can be found in between or bonded to the polymer layers, which are a problem and right now cannot be effectively processed by compatibilization, but this is something we're looking into as well. So how is it done? So actually the compatibilizers, as I said, are chemically designed compounds we develop in the lab, and we try and see how these can interact in a chemical or non-chemical way with the polymers in order to increase their immiscibility. So this can be done in an additive or non-reactive way, or through reactively synthesizing bonds in situ across the contact interface during the blending process. The second point I'm going to talk is about chemical recycling. Chemical recycling, which can also be named as feedstock recycling, is the process leading back to the decomposition or degradation of plastics back to their building blocks, the so-called monomers, or also other valuable low molar mass fragments that can be used for various reasons. It's a procedure that is very popular right now in the academic and industrial world and has the potential to be profitable, reduce the energy and feedstock demand, and close the material cycle. What is it about and how can it be done? It involves depolymerization, the inverse of the polymerization reaction, usually mediated in organic or aqueous media under optimized temperature and pressure conditions, and usually it is aided by catalysts. So this is the process of going back to the actual monomers used for the production of the plastic. A second method, which is termed chemical recycling, is the pyrolysis or thermal cracking, which is basically a procedure in which plastics are being heated up in really high temperatures in the absence of oxygen, which usually leads to the production of char and oil products used for fuels. So this is something that we don't recommend at Imperial, so we just focus on depolymerization reactions. So moving on, and for on depolymerization reactions, as I said, it's a process, it's a chemical process that enables the recovery of the monomers, the building blocks of the polymers, in polymerization grade purity and high yield. So essentially, it gives us enough material in a good state to be able to be repolymerized again into plastics, into new plastics with the same quality and functionality as the original materials, or with the possibility of becoming other high-value products depending on the desired application. Right now, depolymerization reactions are preferentially applied to the polyester family, which are PET, polyethylene terephthalate, polycarbonates, or PLA. That is, one can find it in plastic cups. Polyamides, which are really hard and soft materials, such as nylons, or formaldehyde resins or polyurethane foams as well. So if you look at the graph here, one can see that chemical recycling is indeed one of the most sustainable methods currently applied in the industry as well, but research in the academic world. And because it provides, as a result, it provides chemical products which are of high value and ready to be reused for the production of new plastics. The third and final point of my talk is about new smart plastics. So what do we mean with that? One can talk about biodegradable plastics. So biodegradable polymers can be found in the industry right now. These are plastics that can be degraded by enzymes, or they can be hydrolyzed into simpler building blocks such as carbon dioxide, water, methane, or other organic salt components. This obviously leads to a closed circular ecosystem. For example, a major example of this family of biodegradable polymers is polylactic acid that is currently being used for the production of disposable plastic cups found at Starbucks or wherever. It's important to note that usually with biodegradable plastics, we can talk about bio-derived or bio-based biodegradable plastics as well, where the biomass is used as the renewable raw material in order to synthesize these polymers. So actually, bio-derived and biodegradable are two separate terms that can be combined, but not always. It is important to recognize that some petrochemical polymers can be biodegradable, but are not, and that all not bio-derived polymers can be biodegradable. Except biodegradability, one can talk about the newer generation of materials and plastics that are currently being reported in the literature, which essentially we're talking about degradable polymers which can inherently change their structure. So we can talk about installing chemically responsive switches into the materials, which can't be tripped at the end of their life in order to trigger their degradation or to enable their reprocessing or chemical recycling. This is a technology that is reported right now, and it is applicable to both thermoplastics and thermosets. And we can talk about hydric materials as well, which combine linear or branched polymers via reversible physical bonds, such as hydrogen bonds or ionic interactions. So because the trend of production of these materials in the literature in the past few years has been tremendous, they have been named. So we can talk about covalent adaptable networks now, which is the desirable combination of a cross-linked polymer structure, which has the capability of trigger its reversion from a cross-linked network to a non-cross-linked network. So with this, I conclude my talk. I want to start thanking the people who have been working in the lab with These are Professor Dirk Bitovsek, Dr. Brandt, Talbot, and Dr. Romain, which have been my supervisors this year at Imperial College. I also want to thank Arturo and Manu for working together and producing this very interesting briefing paper. I want to thank the UKRI and Imperial for letting us do the research. And if anyone wants to ask me any questions, I'm online all the time at LinkedIn or Twitter. This is my email address. And I want to thank you all for attending.
Good afternoon. Thank you very much, ladies and gentlemen. And I'd like to first off thank Arturo Castillo and his colleagues at the Ocean Plastics Solutions Network and Institute for Molecular Science and Engineering for inviting me to speak this afternoon. I'd also like to thank the previous speakers for their contributions. So before I get started, I wanted to just outline who RAP are, to summarise the work we're doing on plastics, and then talk a little bit about the report that's been launched today. So first of all, who are RAP? RAP is the Waste and Resources Action Programme. We're a global charity who are working to reduce waste, improve recycling, and create a circular economy in the UK and internationally. We work on all waste streams, but we've got four main priorities. The first of these is tackling plastic pollution. The second, preventing food waste. The third is to increase the sustainability of clothing and textiles. And the fourth is to improve waste collections and recycling. Looking at our work on plastics, this largely falls under the banner of the UK Plastics Pact. It's a voluntary agreement which aims to create a circular economy in plastics in the UK by 2025, with the ultimate endpoint of eliminating plastic pollution. The Pact's got 85 business members from across the UK plastic supply chain. Between them, they account for 2/3 of consumer plastic packaging in the UK. There's also another 42 supporting members, people like trade associations, government departments and charities who don't make or use plastic packaging themselves, but who are relevant to the debate on plastics. There are four targets under the Pact to be achieved by 2025. The first is to eliminate problematic or unnecessary single-use plastic packaging through redesign, innovation, or reuse delivery models. The second is that by 2025, 100% of plastic packaging on the UK market will be reusable, recyclable, or compostable. Third, we want 70% of that packaging to actually be recycled or composted by 2025. So it's not just about the theory of whether it can in theory, but also whether it actually happens in practice. And the fourth target is to achieve an average of 30% recycled content incorporated in plastic packaging. That's all about closing the loop so that you don't just collect plastic packaging for recycling, but once it's recycled, it goes into new products and creates that circular economy. I very much welcome this new report. It's really important from our point of view that if you're going to solve this problem, you start from an evidence-based approach. So research such as this is absolutely vital. It's also really important to recognise that though the ultimate problem that we're all talking about is plastic pollution in the ocean, that's not where the problem starts. The problem starts on land, and it starts with material being made, created into plastic, particularly plastic packaging, and then not being effectively collected and recycled. So what we need to do is we need to start at the beginning of that chain and solve the problem through improvements in design of packaging, by eliminating worst kinds of single-use plastics, and then improving the durability and recyclability of the plastic that we have left. So from our point of view, what we need, and what research such as this does a really good job of adding to that debate, is we need research that's across the whole of the plastic supply chain and across all the different types of technologies that are necessary to improve the situation. So we need to, as I say, improve durability and recyclability. we need to deal with the different kinds of plastic that are going onto the market, and we need to deal with it from the design stage through the manufacturing stage to the recyclability at the end of it, the collection, recycling, and turning it into new plastics. As well as the technical side of that, we also need work on the policy side. There's been a lot of discussion in the UK context over the last couple of years about plastic recycling, particularly in the context of DEFRA's resources and waste strategy. And there are policy ideas in the pipeline to improve the situation. But we need to have ongoing discussion about the policy solutions that might help us to improve the technical situation as well. So from my perspective, this report is a really good contribution to that debate, because it looks across the whole piece from the start of the supply chain to the end, from different kinds of technologies that affect the end points, and it also looks at the policy issues that are important. So I very much welcome this report. I think it's a really good contribution to debate, and I look forward to discussing the report and where we go from here with the other contributors in the rest of the session. Thank you very much.
So I'm Tanya Ferry, I'm Head of Environment for the Port of London Authority, and I've been asked to talk at this prestigious event about the litter that we find in the Thames. Just a quick note of who we are and where we operate. This slide shows a number of different pieces of work that we do across the Thames. We manage it from Teddington right out to the ocean and sea in the east, by a number of different manners on the water, by guiding through pilotage, by carrying out surveys, and remote monitoring through our vessel traffic services. The port itself, if people aren't familiar with it, carries a huge amount of cargo. We're the second largest in the UK. Around 50 million tonnes. Your cars, Pringles, fuel, and fridges and freezers. New Zealand lamb and wine will come through the port, mostly to the east, but in central London there's quite a lot of activity for the tourism trade and bringing cargo straight through into the west of London and London's waste back out. It's also a thriving environment. We have 126 species of fish, over 1,000 seals every year, and 300,000 overwintering birds using the estuaries, features and habitats. So it's really important, and it's heavily protected as in reflection of that. As I mentioned, there's quite a lot of recreational and amenity aspects to the river. People come from worldwide destinations to see the features along the Thames, but also the Thames itself. And most famously in 2012, it was the site of the Jubilee pageant, where there were over 1 million people on the water and many more millions watching from either their screens or from the sides. It's also a cruise destination, so we get international visitors coming in as far as Tower Bridge, and also in Greenwich, which is the picture here, as you can see the Cutty Suck. So it's an area that people want to come and see and want to enjoy. It's also well used by the locals. We find now since lockdown a lot more people are coming to use the Thames as a place to find some space, clean air, and watch some wildlife. But in order to keep that clear, we have operated a Driftwood service for a number of decades. It was called a Driftwood service. We still use that name because of the type of items that we used to collect. It was predominantly wood. But more recently, it is plastics that we are collecting. So the tonnage that the weight of what we collect has gone down significantly, from thousands of tonnes to around 200 tonnes a year. But the volume remains the same because of the light plastic content that we have. If we were to containerize the amount of plastic we collect, we would be able to reach the top of the Canada Tower at the Isle of Dogs, or if we were to put it in the new route masters, we would have from one end of the Blackwall Tunnel to the other full of buses. So there's quite a lot of material that is then taken away and recycled. Most of that is collected through this way on a floating collector. We have about 11 of them moving between Putney and Greenwich. We site them based on the flow of the river, where they're most effective to collect the litter that floats on the surface without interfering with the navigation, and our team will come and empty them and then dispose of them at a riverside recycling centre. 96% of it is recycled, but it does need to be mixed with virgin plastics, so it isn't recyclable on its own because of the deterioration, and some of that plastic has been there for a number of decades. There are also foreshore cleanups. So there are hundreds of thousands of volunteers that are willing to put their welly boots on and come and clear the areas. We do it as staff. We also support Thames 21, who clear the foreshores right from Putney down to Rainham in Essex. Run a Cleaner Thames campaign to try and raise the awareness of where and how the litter ends up in the river. You can see here with Paul Rose, National Geographic Explorer. There have been plastic items found in the stomachs of animals now on the Thames. We find it comes from all sorts of different places, whether it's washed in through drains or being left on the side of a path, blown in or deliberately dropped. Effectively, if it's not put in a bin and it's not put through the system properly, it may end up in the Thames in London because of the drainage. And so this is why this project and the paper is really important. If we can stop by finding a better system that stops the litter even necessarily needing to go in a bin, and incentivise people to put it back into a system that is closed loop, we would hope that we will see less and less of it on the river. Thank you very much for your time.